Yeah, pretty much.
Thank you very much.
Thank you very much as well. Good evening, ladies and gentlemen. And we just heard that obtaining fracture toughness values from welds can be a minefield. So here's the minefield. Basically, what I'm going to do is I'm going to analyze a reactor pressure vessel steel weld by the master curve concept, and also use a local approach and just compare what the assessment methods say for various loading rates. Something really interesting happens there, especially at higher loading rates. So just a bit of background on the material, the specimens, and the testing. So we used a unused reactor pressure vessel, Biblis C in Germany. The material can be seen up here. Most of you who are dealing with this type of subject might know it. We extracted large bending specimens, 40 by 20, from the weld with 10% side grooves. We fatigue pre-cracked them according to ASTM E1921, and we also performed fracture mechanics testing according to the same standard, and also E1820. And I have down here an image of the reactor pressure vessel wall. It's a pretty large structure, which allows a pretty good extraction technique of the specimens. You can see here the thickness of the wall is about 250 millimeters, and this is a hardness profile measurement. And you can see that there's a pretty good region where we have constant hardness properties, and that's where we extracted the bending specimens. As you can see here, we have 4 layers. So up top, we can see a matrix of the database that we generated. It's quite extensive, actually. So what we did was we tested from 1 megapascal root meter per second, which is quasi-static, up to about 10 to the power of 4, which I would consider moderately dynamic or elevated loading rates. And you can see here the amount of specimens that we tested per test series. So we always have 2 temperatures in the ductile to brittle transition region, and especially for the quasi-static testing conditions, we have a bunch of specimens, which allows us to make some really powerful conclusions. Okay, so just so everybody's on the same page with the assessment methods, I'm not going to get into too much detail on the master curve, because I think most of you who are interested in this topic know how it works. But a few points I still want to pinpoint. So basically, we have a Weibull distribution up here, which describes the scatter of the results here, and we have parameters such as P, which is the exponential relationship, which describes the temperature dependency of the median values here. The parameter P is set to a value of 0.019 in the standard. It's just been fitted to the database of most ferritic steels. We also have the parameter T naught, which basically shifts the master curve on the temperature axis, and it basically dictates what your toughness is of your material. So this is not part of the standard, but recently there's been a lot of research going on to how the master curve fits under elevated loading rates, and it was actually found that the master curve doesn't match the experimental results very well if we increase the loading rate. And we can overcome this discrepancy quite well if we increase the shape factor P, which is basically the slope of the master curve here. And it has been proposed to adjust this value to a value of 0.03, and I will refer to that as the dynamic master curve. This will be important later. Furthermore, the newest version of the standard also includes the inhomogeneity analysis, where basically, because this is a weld, this is important, the analysis can tell you, is my database potentially inhomogeneous, and if yes, you can use alternative distribution functions such as the bimodal or multimodal distribution function instead of the classic Weibull to describe your data. I'm not going to use the classic master curve description, as you can see here, because of the local approach, which I will introduce later. I would furthermore introduce or use the accumulated probability of failures. You can see here You can get that really easily if you just shuffle around a few equations. Basically, so you have the accumulated probability of failure as a function of the load, KJC in this case. And what I did is I can rank the experimental data with rank probability. This is always the median failure probability of the experiments, the icons. And you can also calculate the error bars, 5 to 95%, as just kind of an orientation of how exact your predictions then are. Just really quickly, the local approach thing. I know this is a very complex topic, and I could talk about this in a different presentation, but just the basics of it. So we don't rely on macroscopic parameters such as K here to assess fracture, but we want to actually use real physical mechanisms to describe failure in the material, and by that we use local stresses and strains, which we obtain by doing rather complex FEM simulations, as you can see here. So I simulated this is 1/4 of the bending specimens, as you can witness on the left. Important in this context is because we have slightly elevated loading rates, that we explicitly consider heat generation and also heat conduction, because it's not enough to just consider or flip the switch in Abacus or whatever you're using, give me adiabatic heating conditions, but because we're actually not that fast, heat can be conducted away from the crack tip, and that actually has a huge impact on the temperature distribution. So I'm going to skip over this part. In the middle basically just states that you need to somehow compare your experimental with simulation results that they produce the same output in terms of force displacement, but also force time, or in this case K over time. And the local approach model that was used was a model proposed in 2010 from colleagues of mine, which is basically a more sophisticated Barama type model, and it describes the change in probability of failure as a function of two terms. So you have the nucleation of microdefects and the instability of microdefects. The nucleation term is governed by plastic strain and by stress triaxality, and the instability term, as you might expect, is governed by the maximum principal stress. In this case, this is a exponential distribution of the microdefects. So we use, as always, we use weakest link statistics to calculate the failure of the entire structure, and we use it to calculate the accumulated probability of failure. So these diagrams are very complex. That's why I made them very large and put nothing else on the slides. I hope you can see them in the back. But basically, these are the results for the quasi-static testing conditions, and you can see here the probability of failure as a function of K, and you have two series in this case. Two test series exactly. And the solid line is always the standard master curve evaluation, as you can see here. In this case, it matches these results quite well, little unconservative, but here we're not conservative at all. Then the inhomogeneity analysis allows us to do bimodal, multimodal analysis. This is the dotted and the dashed line. They're usually very, very similar, and they're close to each other. In this case, they're up here. So compared to the solid line, we have a better estimation of what's happening experimentally. And what's very, very important is that we are conservative. For the test series at -100 degrees Celsius, we get a better approximation of what's happening as well. Just for your information, I also added the dynamic master curve. It doesn't really make any sense because we're testing at quasi-static testing conditions, but you can also see here that the dashed dotted line, it really doesn't make any sense. It's even outside of the error bars. Here it matches quite well, but that might just be random in my opinion. Last but not least, you can see the local approach, which is the pink line or magenta. And in both cases, you see that the experimental results are described quite well. Here you can see that because we don't have an underlying inhomogeneity distribution in the local approach, we don't get really exact results here, but nevertheless, it's better than the standard approach. Okay, so what happens if we increase loading rate a little bit? I would characterize this as very slow. So we're at 100 MPa root meters per second. We see the solid line, which is the standard master curve approach, here matches quite well, actually. In this case, at negative 80 degrees, we are not conservative again, so it doesn't work in terms of assessment that well. The alternative distribution functions, the dotted and dashed lines, very similar here again are a better assessment method compared to the standard approach here as well. And the dynamic master curve, the dashed dotted line here is not conservative, but still within the error bars. And here it actually matches quite well. Again, I think that is more of a coincidence. The local approach here in pink matches the experimental data quite well. So we're getting a bit faster. We're at the, I would call, slow crack tip loading rate of 1,000. First obvious thing is we don't have inhomogeneity in this data set. This is most likely a coincidence. So in this case, we have the standard master curve approach here, matches the experimental data quite well. In this case, still a little unconservative, but now within the error bars. The dynamic master curve, which is the dashed dotted line, ends up being a bit better fit now, but you can still see here that it's not quite ideal. Here it's pretty good. And the local approach again is very accurate, even though it's a little bit over conservative here at the beginning, but it's still overall very predictive. Now the very, very interesting part, where we have the moderately fast loading rate, we see something very interesting. So again, we start at the standard master curve, solid line, not a bad approximation for the green series here. Here, very unconservative. We don't want that. But we actually see now that if we take the dotted and the dashed line, which is the alternative distribution functions, we see here that it's pretty far off, actually. It's outside of the error bars. It's better than the standard evaluation because it's more conservative. But even you can see here that it's right at the edge of the error bars, and up here, it really doesn't match the experimental results at all. And for the first time, we see that the dashed dotted line, which is the dynamic master curve, is actually the best fit for the master curve methodology, which is this one right here and this one right here. So there seems to be this trend that if you increase loading rate, the standard master curve gets less accurate and the dynamic master curve is more favorable. Overall, the local approach is able to capture everything quite well. So the question is, why is this happening? So again, I could talk about this in detail all day long, but basically it can be linked to two effects. One is very obvious, that is adiabatic heating, and the other one is not so obvious, that is local crack arrest. And just to kind of give an idea of what we're dealing with here, so if we have the highest crack tip loading rate, I calculated numerically the temperature gradient as a function of the crack tip here. And if we just assume right now, of course we don't know where initiation occurred, but let's just assume that it's about 300 micrometers away from the crack tip, then you can see here that by these calculations you can see a temperature shift of these initiation spots of about 10 to almost 20 degrees Celsius, depending on how high you get. And so it's easy to see that the distribution here can be severely impacted. And this, of course, is more relevant the higher your loading rate gets. The local crack arrest is a different topic, and basically you can witness that if you look at the fracture surface. So what you can often see here is cleavage fracture islands, which basically means that you had cleavage fracture sometime during the loading here. You don't know when, but it arrested. These are several hundred microns in diameter. And that means that because the crack arrested and blunted, initiation has to occur somewhere else along the crack front. And because load goes higher and higher, initiation occurs at a higher K value as well. And here again, you can easily see that this can affect or impact the distribution function because global failure is postponed. Now, that's already the last slide, exactly. So summary and conclusion. We saw that for quasi-static testing conditions, the inhomogeneity analysis shows improvement of the assessment method compared to the standard evaluation. The dynamic evaluation is very inaccurate for obvious reasons. Generally, the bimodal and the multimodal evaluation method gives a better assessment than the standard evaluation, even if you increase the loading rate. But generally, you could also see that the agreement of these master curve evaluations decreases systematically with an increase of loading rate, and contrary, you see that the dynamic master curve evaluation, the appropriateness of this increases systematically. And the reason, or my interpretation why this is the case, is that so we have these three mechanisms. We have inhomogeneity, which is linked to microstructural variations within the microstructure most likely, and this is something that widens the distribution function. And then if you have these additional mechanisms such as adiabatic heating and crack arrest, these are both things that squeeze the distribution function further. So if you increase loading rate, then these counteract these statistical implications of the material inhomogeneity, and they therefore get neutralized. Generally, local approach shows a better agreement, but it's more than expected because it also considers heat generation and also has a couple more parameters that you can use to adjust. This should be the last slide. I just want to really quickly thank the German Ministry for Economic Affairs and Climate Action for funding this project, and I would also like to thank you for your attention.
Thank you.